Hey guys, I'm back. So let's start with some properties of limit of function. Let's see. If limit extends to a, fx equal to L, then fx is bounded in the neighborhood of x equal to a. Since limit extends to a, fx equal to L. Property 2. Limit extends to a exists, then it must be unique. Obviously, it can be proved that if you take two limits of fx, L1 and L2, then you will get that L1 equal to L2. You can see it in your textbook, so I just skip this proof. Okay. Next, if limit extends to fx equal to L, limit extends to a mod of fx equal to mod of L. Next, limit extends to a b is equal to b. Here fx equal to b, which is a constant. Then we will get L as b. Okay. Again, limit extends to a x square equal to L square. Here fx equal to x square. Okay. Next, limit extends to a 1 by x equal to 1 by a. Obviously, a not equal to 0. Okay. And now, this is an important property. This is called algebra of limit. Let's see. Let f and g be two functions defined at an interior point of a of its domain D, and limit extends to fx equal to L and limit extends to a gx equal to m. Then what will you get? Limit extends to a f of x plus minus g of x equal to L plus minus m equal to limit extends to a fx plus minus limit extends to a gx. This is number 1. Now, limit extends to a fx into gx equal to L into m. What is L? Limit extends to fx and m, limit extends to gx. Okay. Now, limit extends to a fx by gx is equal to L by m. What is L? Limit extends to a fx by limit extends to a gx. M not equal to 0, obviously. Otherwise it is undefined. So these all we can prove, but I just skip this proof. You will get this in your textbook, so just read those in your book. Now we go to the next topic. Let's discuss about Sandwich Theorem. What is Sandwich Theorem? This is very important theorem. You have to remember it very well. Now, let's discuss. Sandwich Theorem. If fx, gx, hx be defined in a certain neighborhood and fx less or equal to gx less or equal to hx, also limit extends to fx equal to L, limit extends to hx equal to L, then limit extends to a gx exists and is equal to L. Okay, this is very easy to remember. Just this one and these two, then we will get this result. Okay, just remember this, which is very important, and it helps to find out many results. Okay, so let's discuss some properties. F is monotonic increasing function they defined on AB, and A less or equal less than C less than B, not equal to, only less than. Then f of c plus 0 and f of c minus 0 both exist. You have to remember this one. And now the second property is f is a monotonic decreasing function defined on AB, and A less C less B, then f of c plus 0 and f of c minus 0 both exist. Just the difference is here. If increasing or decreasing function in a closed interval AB, then and also A less C less B, then just two of this function both exist. Okay. You can say this: if f is monotonic function, then it can be shown. Okay. Now we will go to some example. This is the question. Limit x tends to 0, sin x by x equal to 1. Prove this. Now, how we will prove this? Let's see. Here, what is fx? This one is fx. Okay. So, first write this as the function fx equal to sin x by x. Okay. Now where it is defined for all x belongs to R. Yeah. Obviously x not equal to 0. Okay. So we will discuss here that the function fx is defined for all x belongs to R. X not equal to 0. Okay. Now, what is the limit point? Here, the limit point is 0. So, 0 is a limit point obviously of the domain okay. Now we have to consider something. Okay, for 0 less x less pi by 2, we can say that sin x less x less tan x. I think you have proved this, so I just keep this. Okay, if it is increasing, then we can say that since sin x function sin x greater than 0, if sin x greater than 0, then what we can see that 1 less than x by sin x. Okay, 1 by cos x. This is number 1. So from where we will get this? This only this here. If you divide this inequality by sin x, then we will get this. Yeah. Here we can easily apply Sandwich theorem. Okay. We already see that limit x tends to a, b is equal to b, where b is a constant. Then if in this function I apply limit x tends to a or limit x tends to 0, obviously here a is equal to 0, then what will we get? 1. Then I can see that on this part the function has a limit 1. Then if I can prove that here on this function the limit is 1, then I can easily say on this the limit is x of limit x tends to 0, x by sin x equal to 1. Okay, so let's try to prove this one. We now prove that limit x tends to 0, cos x is equal to 1. if I can prove that limit x tends to 0 cos x is equal to 1, then I can easily prove that limit x tends to 0 1 by cos x is equal to 1. How? We have seen limit x tends to a, 1 by x is equal to 1 by a. So I can prove this. Okay, so let's start. For fx minus l cos x minus 1 is equal to 2 sine square x by 2. Okay, now I can write this easily. This is less than epsilon. If 0 less than mod of x less than root 2 into epsilon less than pi by 2, just modify this one. Okay, then we can say this. Just from here, mod x less than root 2 epsilon, we just take square and then we can see this. Yeah, therefore limit x tends to 0 cos x is equal to 1. So by Sandwich theorem, limit x tends to 0 plus. Okay, first take this, limit x tends to 0 plus. Therefore limit x tends to 0 plus sin x by x equal to 1. Just 1 by x is equal to 1 by a. Limit x tends to a, 1 by x is equal to 1 by a. Okay, now if x tends to 0 plus is proved, then we have to find out limit x tends to 0 minus sin x by x. Otherwise we can't see that limit x tends to 0 is equal to sin x by x is equal to 1. Okay, so prove that. Now limit x tends to 0 minus sin x by x. If I replace this, okay, now please replace this one, x is equal to minus y. Okay, minus y. Then what will happen? Y is equal to 0 plus. Okay, sin minus y by minus y. Now sin of minus y is equal to minus sin y and minus y. Then minus minus is disappeared, and then what will we get? Limit y tends to 0 plus sin y by y. Already we have proved this is equal to 1. So here we can prove that limit x tends to 0 minus sin x by x is equal to 1. So from this 2 and 3 we can easily say limit x tends to 0 sin x by x is equal to 1. From 2 and 3, or let's write this. 2 and 3, limit x tends to 0 plus sin x by x is equal to limit x tends to, since sin x by x is equal to 1. Okay, now let's move to the next example. Now let's see the next example. This is the question. We have to prove this limit x tends to 0, x sin 1 by x is equal to 0. Okay. So how we can do this? First, you can do this in 3 ways. Okay. First, type 1. Now, here fx equal to x sin 1 by x. Let this is gx and this is hx. Okay, then gx into hx. Here hx is defined for all x belongs to R, x not equal to 0. So if hx is defined here and x is also defined for all x belongs to R, then we can say fx is also defined for all x belongs to R, x not equal to 0. Therefore 0 is the limit point of the function fx. Now let D is the domain of the function fx. Okay, what is domain? R minus 0. So let D, therefore now we have to prove hx minus 0. Here sin 1 by x minus 0. Okay, so or we can say mod of hx. Therefore mod of hx is equal to mod of sin 1 by x less or equal to 1 for all x belongs to D. From this what we can say, hx is bounded in every neighborhood of what? The domain D. This is bounded. It is clear. Now we have to show that what is the limit of the function. Okay, what we can say, therefore limit x tends to 0, gx is equal to limit x tends to 0, x is equal to 0. Now if we evaluate this fx, limit x tends to 0, what will we say? Gx into hx. Limit x tends to 0, gx into limit x tends to 0, hx. Okay, so 0 into limit x tends to 0, sin 1 by x is equal to 0, because 0 into something we get 0. Here we don't have to prove the limit x tends to 0 and sin 1 by x, that is what is the limit of hx. Okay, this is method 1. Now type 2. Here minus 1 less or equal to sin 1 by x less or equal to 1. we can say for any type of theta, here theta is equal to x. Now for all x greater than 0, we can say minus x less than x sine 1 by x, less or equal to x. And also for all x less than 0, if x less than 0, then obviously the sign will be positive. Then what will you get? Here x minus x. Okay, so from these two, this one and this one, what will we say? That mod of x, so minus of mod x less or equal to x sine 1 by x less or equal to mod of x. Now limit of x tends to 0, mod of x is equal to 0, and also limit x tends to 0, minus of mod x is equal to 0. So by Sandwich theorem, what will we can say? Limit x tends to 0, x sine 1 by x is equal to 0. This is the second method. Now type 3. You will prove this by epsilon delta definition. Okay, what we have learned in the first lecture. If you haven't seen this, you can go to the I button. Now let's start type 3. So first we have to choose an epsilon greater than 0. It is given, obviously. Let epsilon greater than 0 be given. Now we find a delta greater than 0 such that, what is mod of fx minus L? So what is your mod fx? X sine 1 by x minus 0 less than epsilon whenever 0 less than mod of x minus a, that is 0 less than delta. Now we have to evaluate this one. Now mod of x sine 1 by x so we can easily say that less or equal to mod x, since we know that mod of sine theta is equal to less or equal to 1. So here mod of sine 1 by x less or equal to 1, that is less than epsilon whenever 0 less than mod of x minus 0 less than delta, where delta equal to epsilon. This shows that limit x tends to 0, x sine 1 by x is equal to 0. Okay, this is proved. This is one type. Okay, you can easily prove that limit x tends to in the same way. Limit x tends to 0, x cos 1 by x is equal to 0. Okay, limit x tends to 0, x square sine 1 by x is equal to 0. Limit x tends to 0, x cube cos 1 by x is equal to 0. In general, what we can prove? Limit x tends to 0, x to the power p sine 1 by x or cos 1 by x, and x to the power p cos 1 by x is equal to 0, where p must be greater or equal to 1. Okay, so if greater or equal to 1, then we can also prove that limit x tends to 0, x to the power 3 by 2 sine 1 by x or cos 1 by x is equal to 0. Okay, So today I end this lecture here. If this video is helpful, then please hit the like button and share this video with your friends. So goodbye.